Okay, in this video we are going to show that only connected sets in a lower limit topology are singleton sets. To show this, first of all we just recall what is lower limit topology. It is the topology generated by these kind of sets. These form basis and these topology generated by these sets. Okay, the key idea here is that one of the key idea is that our usual topology is a subset of our lower limit. That is, every open set which is in usual topology, it's open in lower limit topology. So in usual topology, we have open sets like this. These form the basis. A, A comma B belongs to real number. So okay, so minus infinity to A is open in R usual, therefore it is open in lower limit. Is open in RL. And since in RL open sets are formed by this, and A to infinity is open in RL. So these are the key facts. We are going to use this. Okay, now I will give you a rough idea. Rough idea is that this is real line and let this is set A. Then let us assume that it has an element, say x. Okay, so we can write A as minus infinity to x intersection A union x to infinity intersection A. Note that this is an open set in A. This is open set in A in subspace topology. Disjoint open set in A with subspace topology. Okay, so these form separation. So any set cannot be connected set because we can find separation like this if it is at some element x. So this is the key. This is a rough idea. Okay, now we begin with the proof. Okay, proof goes like this. Assume we will prove by contradiction. Assume A to be connected. And A comma B, where A is not equal to B, A comma B belongs to A. Okay, A comma B belongs to real numbers such that A is not equal to B and A comma B also isn't that A. We need to show A is a singleton set. This is our aim. We will show that A is singleton A. A is equal to B. This is what we show. We assume that A is not equal to B, and then we will show that A is equal to B by contradiction. Okay. Now again we can write A as from minus infinity to A intersection A union A to infinity intersection A. Now since A is a connected set and these form separation, one of them must be empty. Either this is empty or either this is an empty set or this is an empty set. Okay, now since A belongs to A, we know that, so A intersection infinity intersection A is not empty because it has A, this has A, it cannot be empty. So this must be empty. This is an empty set. Thus we have minus infinity to A intersection A is equal to empty. Now B belongs to A, so B cannot belongs to this, because if so, then B this is cannot be empty because B will belong to the intersection. Thus, where does B must belong? B must belongs to A to infinity. As A is not equal to B, so we have A is less than B. In a similar way, we can write A as minus infinity B intersection A union B to infinity intersection A. Okay, and in same process we can show that B is less than A. This is second. Now just observe first and second. First show that A is less than B, and second show that B is less than A, which is a contradiction. We must have A is equal to B. That's the only possibility. So we have shown that if A is not equal to B and A comma B belongs to A are any two elements, then A must be B. So this implies that A must be a singleton set A. So we have what we have done. We have chosen A to be arbitrary connected set in RL, and with this we have shown that A must be a singleton set, arbitrary non-empty set, and we have shown that A must be a singleton set. Hence proved.